Hello class, this is the Math 11 section 4.1 about more non-linear functions and their graphs. So in chapter 4, we're going to talk about polynomial functions and rational functions. So you need to know what is a polynomial function first. So in order to be a polynomial function, so important thing is the degree. So the degree is, this is a degree. So as long as the degree is here is a whole number, which is we call the degree is a non-negative integer, which means the number that you can see as a 0, 1, 2, 3, 4 kind of number, okay? And then that one we call those are numbers are the non-negative integers, which is non-negative. So that we call the polynomial functions. And then the coefficients is okay to be any numbers. And then the domain of, and also one more important thing is you need to know the leading coefficients. Leading coefficient we call the a sub n. So the first numbers in the first terms. Domain of the polynomial function is real numbers, and its graph is continuous and smooth without breaks or sharp edges. So formulas, which is the constant function. First is a constant function, which is a degree of 0. And the linear functions, the degree of x is a 1. And then quadratic functions, x equals 2, degrees of 2. And then this is a degree of 6. So there's no special name, but still polynomial. And then as a leading coefficients, it's going to be here is a 10 and 2 and 3 and then negative 1/2. So that's what we call the leading coefficient. All right, absolute value and local maxima. So the absolute value on the compared to this graph, the first graph, figure 4.4, there's a the absolute minimum, because that's the lowest point you can see from the graph, but both come with the error, so there's no absolute the maximum this time. But the second graph, this is actually the highest points, and this is the highest, which is hit as the highest, and these are the absolute maximum. This is sorry, this is absolute maximum, but not this one. Not this one. So this is absolute maximum. But we also can say local maximum and minimum. So when this time, actually there is the local, this is a local maximum and this is a local minimum. But there's no absolute minimum for this case because there's errors on here, okay? All right, let's look at the next page. So finding the extrema. So extrema means it could be the maximum or minimum. So extrema also has minima and the maxima. So when you have more than one minimum, we call the minima, and if you have more than one maximum, we call the maxima. So a function may be the several local minima, extrema, but at most the one absolute maximum, and the one absolute minimum. Okay, so it is possible for the function to assume the absolute extremum at the 2 value of x, so which is possible, see, because this is hit the highest place, okay, as a graph. Yeah, so there'll be a the 2 value of x, but cannot be the 2 maximum as absolute, okay. And then the absolute maximum is 11. It is a local maximum as well, because near x equal to negative 2, x equal to 2 is the largest y value. So absolute value and local extrema. So if the C be in the domain of f is the absolute or global maximum. So as long as this is the highest of the any of the x value, absolute minimum, which is this y value is the lowest of the any of the any y value, and the local means hit the highest actually, but it's coming from the turning points. It's from the turning points. All right, okay. Let's look at the other problem. So let's look at the first problem here. So the graph shows the monthly average high temperatures in Daytona Beach. So the identify the absolute maximum or minimum this time. So the absolute maximums, I want to say about here. So I want to say this is, it looks like a highest place, okay? So I want to say this is a maximum, which is absolute, okay? Because there's no other places higher than this one. So absolute maximum in here is about 90 degree, pretty nice. And the minimum, which is about, this is not the, actually the, this is actually ended, right? So you have to look at that as what is it looks like a lowest. So for me is, I think this is the lowest place. So it's not even 70. So I want to say about 69 degree. It's going to be minimum. And then identify the local maximum. So local maximum, which is, yeah, there's no other place in there. So I want to say 90 degree Fahrenheit. Okay, number 2, use the graph to estimate the local extrema and the absolute extrema. So we have to kind of check in the turning points. So there's some points actually that we can think about it. About here and about here. I think this 3 points going to be something that we can talk about, okay? So I want to say there is the absolute minimum, which is the lowest place is the minimum and maximum is all about y value, so negative 12. And there's absolute maximum. Well, both of the ends is arrow, right? So, oh, sorry about that. I'm gonna use another color. Okay, let me use the, yeah, on this place is actually the arrow, right? So I want to say there's no the absolute maximum, but the local maximum. So local maximum is something that is kind of turning in this way, okay? So this place is the local maximum. So I want to say about here, which is this about here. So each one is going to like 3, 6, right? So I want to say about 2.5. But there's also the local minimum, which is which is 2 places. Okay, so here to here. So we already have a negative 12, and also I want to say about 2, a little bit lower than 2.5, right? Yeah. Okay, let's look at another pages. So in the next problem, use the U.S. Consumption of natural gas from the 1965 to 1980 can be modeled by f of x equal to, yeah, those the leading coefficients with the decimals, okay? Where the x equal to 6 corresponds to the 1966 and the x equal to 20 to 1980, 20 to the 1980. Consumption is measured in trillion cube feet. So I want to figure out what is the f of 10, which is, you plug in 10 in the x, okay? So 0.001234 of 10 to the fourth power minus 0.005 689 10 to 10 cube and 0.808792 10 square minus 0.5145 times 10 plus 1.514, and then if I simplify, it's going to be 0.706. So what does this mean? So this means the consumption was 0.706 trillion, that's a unit, per cubic feet. All right, in B, we are looking at the 625, and then 0.4, 0.8, and then each one is a 0.1. So I want to say it's from the 6 to 20, and then each one is coming to the 5 in here, okay? So if I say this is about 1965, which is this is going to be 1970, and this is going to be 1975. Intervals are the 1980 here. And then from here, it's going to be from the 0.4 to 0.8. So 0.4, 0. Up to the 0.4 up to 0.8, which means 0.5, 0.6, and 0.7. And each intervals is a 5 for the horizontal axis, and intervals are 0.1 for the vertical axis. Now we are looking for the describe the energies during this period, okay? And then what happened to here? Actually, the graph was actually maximized up to here, right? So it's kind of increasing up to here. And then from here, start decreasing when hit about here. So what is the point could be? I want to say about 1971. And this place, okay, I want to say that 1978. And after 1978, it start increasing again. So when I explains it, it's going to be the graph increased and reached a maximum and decreased it and reach a minimum and then increase again. So determine the local extrema and the interpolated result, okay? So the local extrema, so I want to say there's a local maximum will be when 1971 and is about 0. Little bit more than 7, so 0.73 trillion and cubic feet. And also the local minimum will be about 1978, and then it's gonna be about here to get 0.51 trillion cubic feet. That's actually the natural gas consumption, okay? All right, let's look at the even symmetry. So even symmetry means when you look at the graph through the y-axis, okay, so this axis, okay? When you look at the y-axis, if you see that the reflection, so one side to the other, that's what we call the even symmetry. So even functions, which is whatever x you plug it in, and then your y's always come out the same. Okay, so that's what we call the even functions, which is symmetry with respect to the y-axis. And then the graph is odd function, so it's the symmetry with respect to the origin, which is you get you got the idea about that, okay? All right, so let's go to the asymmetry. It's going to be the forms of this one. So it's symmetry with respect to the origin here. So origin, see that? All right, odd functions. So odd function is odd functions f of, previously, I think I shouldn't say this one. I think that I messed up in here. So function is even functions. If the f of x equal to f of negative x, okay? And then graph of the even functions is symmetry with respect to the y-axis. Sorry about that. So this is a correction. So that's a graph of the even functions. There's a mistake here. Sorry about that. And the odd function is the symmetry with respect to about the origin. Okay. So odd functions is gonna be about this form. And then it's a symmetry with respect to the origin this time. All right, now identifying the odd or even function we have. So in here, so terms of odd and even have special meaning when they are applied to a polynomial function f. if f of x contains the terms that have only odd power of x, and then function is usually odd function, and then the function contains the only even power of x, and then usually this is an even function. So let's look at the example for each of the representation of a function, identify where its function is odd, even, or neither. So in this time, okay, so what I want to say is, okay, I want you to look at what happened for the y value. So when you look at the y value, so 0 is in the middle, and then as you notice, okay, y value also changing, right? When x value changing, also the y value is also changing, okay? So when x is going to -2, -1, 0, 1, and 2, and the y value with the sign come out the same, it's an even function, but y value is also changing as a sign too, right? So because of that, this is odd functions. For the number 2, the graph is actually the symmetric about the y-axis, as you notice here, right? So, but even though x is a different sign, y is always come out the same number. Did you see it? So these functions we call the even function because it's a symmetry with respect to the y-axis. All right. So now when you have real functions, and then now you can check with the degree. So degree of the first term is 4. Degree of second is 2. And also the when you have a constant is always degree of 0. Which means 4 to 0 is all even number. So it's an even function. Also, when you plug it in negative x into the function, and then it still come out the same as original. Which means f of x same as f of negative x. So because of that, it's an even function. And then f is the square root of function. So let's say square root of function is square root of x. So if you plug it in f of negative x, I don't think the square root of x is the same as square root of negative x. Okay, so f of x is not same as f of negative x, which is not even. Now for the odd function, f of negative x same as negative f of x. So f of negative x and square root of negative x, and then negative square root of x. Of course, it's not the same either. So not odd. So square root function is even, nor odd. Okay. All right. Let's get another. Oh, it's the same problems actually happened twice. Okay. Oh, that's all. That's all for this. Okay. So thank you for listening.